A lot of acid-base reactions require us to do some calculations with them. So, well, we're going to look a little bit at what are acid-base reactions, and then we'll do some of that calculation stuff with doing some titration calculations. All right, so when I look at an acid-base reaction, I am looking at a situation where I typically form some sort of a salt and water. Now we call them neutralization reactions because we are neutralizing off the acid or the base as we combine them. However, the resulting solution is not always neutral. All right. The hows and whys of that, if you go on to take second semester general chemistry, you'll actually understand aqueous ionic equilibria in far more depth than we covered in this class even. And you will learn about what happens when you have like a strong acid, strong base, or a strong acid, weak base, or a strong base, weak acid, or a weak, weak situation that, you know, at the equivalence point, what is your pH? Is it 7? Is it 11? Is it 5? All right, and so the hows and whys of that you'll explore in more detail in a subsequent course. But just when we say neutralization, we don't necessarily mean that we are getting to a neutral solution, but we are neutralizing the acid and the base that we initially put in there. Okay. Hopefully in your prep chem class, you learned that there are three main acid-base definitions. The one that we use a lot is the Bronsted-Lowry definition, where we look at an acid or a base as a proton donor or a proton acceptor. Okay, and so our acid is a proton donor and our base is a proton acceptor. And that's why we can get things like the autoionization of water occurring, is because water can both accept and donate a proton. So it can act in an acidic capacity or it can act in a basic capacity. Okay. All right, so let's take a look here. I'm not going to put out the entire solving of this equation. I'm going to give you a few things, but this is for you to try out on your own. This is like what we covered in the previous lecture video where we did the solution inventory. So notice that normally I want you to try stuff on your own, because if all you ever do is just copy down what I write, then you're not going to actually learn it. So here I've got a limiting reagent problem that is going to be an acid-base reaction that has some pH considerations, all right? And if you forgot the pH stuff from your prep chem class, I put the equations here on this slide. So you've got some sulfuric acid and some potassium hydroxide. You want to determine the concentrations of the ions in solution. So this is that solution inventory. Okay, so solution inventory, and then figure out the pH and the pOH. So this is a good check to see if you remember how to do some of the stuff from your prep chem class as well. So again, I'm not going to give you the whole thing. I'm just going to tell you some final answers. All right, so your unbalanced equation is going to be sulfuric acid, your potassium hydroxide, okay? All right, so you'll want to balance that before you start off, okay? And then what I will give you is I will give you the final answers for the solution inventory. Okay. And then your sulfate is going to be okay. All right, so there are your final answers for that solution inventory, okay? Now, I will also give you the pH and the pOH, so you can check your calculations on that. Now, looking at this, what do you think you're going to get for the solution? Do you think the solution is going to be acidic or basic? Because we didn't actually do a full titration here. If we just dumped 2 aliquots of this stuff together, right? We're going to run out of one before the other, but we'll still have some stuff left over. A true titration, we would be controlling it very carefully. All right, so what do you think we're going to get, an acidic solution or a basic solution? If you said basic, you're right, because our hydrogen ion is our limiting reagent, which means we've consumed all of that, and we simply have excess hydroxide in solution. So our pH is going to be 13.0043, and our pOH going to be 0.9957. So a fairly basic solution. Okay. All right. Now, let's just take a look at some basic stoichiometry with titration. So I've got a carbonated soft drink, or a non-carbonated soft drink that's got some citric acid in it. We need a certain amount of sodium hydroxide to neutralize it completely. What is our concentration of that citric acid that was in our soft drink? Okay. All right. So what's our first step? Balanced equation. All right, so there's our citric acid, sodium hydroxide, sodium citrate, all right, now looking at this, how many hydrogen ions do I have in front of my citrate anion? I have 3. Citric acid is a triprotic acid because it has 3 acidic protons that can come off. Okay, so how do we go about doing this? How do we figure out what our concentration of citric acid is? Well, it says that we had 100 mils of the soft drink and it required 33.51 mils of a certain concentration of sodium hydroxide to neutralize our citric acid. So we're going to say we have 33.51 milliliters of sodium hydroxide. We have 1 liter in 1,000 milliliters. We have 0.10 or 0.01. Yeah, 0.01024 moles of sodium hydroxide in every 1 liter. According to our balanced equation, we have 3 moles of, I'm going to abbreviate citric acid with H3-CIT, okay, over 1 mole, or no, wait, I looked at the wrong thing on my paper. We have 1 mole of citric acid there we go, over for every 3 moles. Okay. So far, so good. And then we want the concentration. So I have a unitless 1, and I had 100 mils over 0.1 liters. Okay. And then all we do is we grab a calculator and we can figure out that we have 1.144 times 10 to the negative 3rd as our molarity of citric acid. Okay? All right, here's another one. We've got a sample that's got oxalic acid and something else that doesn't react with sodium hydroxide. We know how much sodium hydroxide is required to titrate the oxalic acid in the sample. Now we want to know what is the weight percent of the oxalic acid. So we're going to need to take our titration information so we know how much sodium hydroxide it took. If we write a balanced equation, can we figure out how many moles of sodium hydroxide it took to neutralize it, and then how many moles of oxalic acid that translates to? Absolutely. And if we figure out how many moles of oxalic acid we have, can we figure out grams? Yes, we can. Okay, so we need to get grams of oxalic acid so that we can then do grams of oxalic acid over grams of sample to give us our mass percent. So let's take a look at this. Okay, so we're going to calculate the grams of oxalic acid. All right, so we have 29.58 mils of our sodium hydroxide. Okay, and we need our balanced equation here. So if we take our you might recognize, if you took prep chem at Grossmont College, you might recognize oxalic acid as the acid that we used in our titration experiment in our prep chem class. You get sodium oxalate and water. All right, and then oxalic acid is diprotic, so we're going to do 2 and 2. Okay? All right, so we've got our sodium hydroxide. We have a liter for every 1,000 milliliters. Okay, and then we get 0.5501 moles of sodium hydroxide for every 1 liter. We have 1 mole of oxalic acid for every 2 moles of sodium hydroxide. And then we need the molar mass, and so for oxalic acid it is 90.04 grams in every 1 mole. And we're going to get 0.7326 grams of our oxalic acid. Okay? Now we wanted a percentage. So remember, mass percent is the mass of the part over the mass of the whole times 100. All right? So we're going to get 0.7326 grams of our oxalic acid over our, 4.554 grams of our sample times the 100, and we're going to get 16.09% oxalic acid. Okay? All right. Now, here's a puzzle. So, we have an unknown acid. It could be tartaric acid or it could be citric acid. We do a titration and we want to figure out what is the identity of the acid. Okay? So, when I look at these, citric acid is triprotic and tartaric acid is diprotic. So we would have 2 different looks at how many protons when we figure out what is going on with our acid. So what we can do is we can either get some molar masses or we can get the grams of each acid to find the one that matches the amount of acid. Okay, so when I look at these, okay, I see that citric acid, if I calculate the molar mass, it is 192.1. And tartaric acid is 150.1. Okay. So, actually that looks really hard to read. It should be 150. That's better. I do not always have the world's neatest handwriting, as I'm sure everybody's figured out. Okay, so when I look at this, I can figure out how many moles of hydrogen ions that I neutralized with my sodium hydroxide. Okay, so let's take a look at that. Okay, so my moles of hydrogen ions. Okay, I had 29.1 milliliters of sodium hydroxide, 1 liter in 1,000 milliliters. Okay, and it was 0.513 moles of sodium hydroxide for every 1 liter. Okay, and we neutralized 1 mole of hydrogen ion for every 1 mole of sodium hydroxide. Okay, we'll address the stoichiometry and the triprotic and the diprotic acid after we do this. This is just our first step calculation. So that'd be 0.0149 moles of hydrogen ions. Okay, so with that amount of sodium hydroxide, we can neutralize 0.0149 moles of hydrogen ions. So now we have to figure out, did we get those hydrogen ions off of a diprotic acid or off of a triprotic acid? Okay, and so what we're going to do is look at our two acids. Now our citric acid. Okay, citric acid is triprotic. Okay, that was that H3 cit. Okay. So what that means is to figure out the moles of citric acid, we would have to divide that by 3, looking at our moles of hydrogen ions. Okay. Because if we do this in a triprotic, if I have 0.0149 moles of hydrogen ions times 1 mole of citric acid for every 3 moles of hydrogen ions. See how that works? I end up with 0.004967 moles of citric acid. Okay. Now we had some molar masses, and we know the original grams of sample. Our problem told us that it was a 0.956 gram sample. So if I know grams and I know moles, what can I calculate? I can calculate a molar mass. So we can try that. We can take our 0.956 grams of our acid over our 0.004967 moles of our citric acid, and we get 192.483 grams per mole. Now, I said on the previous slide that citric acid had a molar mass of 192.1, so that's actually not bad for an experimental set of data. But let's go ahead and calculate the tartaric and see if what we get is anywhere close to the molar mass of tartaric acid, just so that we can be certain that this is citric acid. But right now it's starting to look like citric acid. So our tartaric is diprotic. Okay. I'm going to abbreviate it as H2 tart. We do a lot of abbreviating in science. All right, so I can do the same calculation. I have 0.0149 moles of hydrogen ions that were neutralized by the sodium hydroxide. And here I have 1 mole of my tartaric acid for every 2 moles of hydrogen ions. And so I end up here with 0.00745 moles. Okay, then I can take this 0.956 grams of our acid sample divided by our 0.00745 moles of the tartaric acid, and I get 128.327 grams per mole. Okay, now I told you on the previous slide that tartaric acid has a molar mass of 150.1. Is 128 anywhere near that? No, it's not. So our acid is citric acid. Therefore, is okay. So we were able to figure out the identity of our unknown acid. Okay, here's another one that I want you to try on your own. This one's a little bit more difficult. All right, so this one and the next slide are going to be challenge ones that I'll let you do as extra notes credits, again, like I did in a previous chapter. So this one's going to be a challenge. Okay, so you're supposed to calculate the molar mass of this particular carbonate and identify whatever the metal is. All right, so see if you can figure it out. I'm not going to tell you. This is going to be one, and this one, the next slide too. I'm not going to tell you the answers this time. These I want you to try, and if you want me to check your work, then I want you to shoot me an email, or if you have me in a live lab class, then I would like you to ask me in lab, and I'll have my notes with me during lab, and I can check your answer. If you're a random person that found my crazy teaching videos on YouTube and you want to know the answer, I guess you could leave a comment. I can't promise that I will see it right away because I don't necessarily monitor YouTube comments very well because I monitor mostly my teaching emails. But you know, if you want to know the answer, feel free to leave a comment on the YouTube video, and when I get a chance, I will try to respond. Okay, so this is a challenge you can do for some extra credit if you are in one of my classes. Okay, same thing with this one. This one's another challenge you can try for some extra credit. It'll just go to the notes category, so because these are part of your notes. So if you want a little bit extra notes credit, I will let you try these two problems and upload your work on Canvas for me, and we'll see how you do.